In this video, we're going to be going over two separate equations. The first three questions are going to be on Kepler's third law, right here. And the last few are going to be on Newton's law of universal gravity. So we're going to jump into it. Keep in mind, I have my calculator right here because we're going to need to do some calculations. So let's take a look at this warm-up question. An asteroid in the asteroid belt takes 4.6 Earth years to orbit the sun. What is its average distance from the sun in AU? So when we're looking at T, that is going to be the period. That is a time. And when we're looking at R, this is going to be the distance from the center of your orbit. So the asteroid here takes 4.6 years to orbit the sun, and what we're looking for is the average distance the asteroid is away from the sun. So whatever we're looking for, I recommend putting it on the top of, make it your A, and whatever make it your B, because it just makes it easier to solve at the end. So the period of the asteroid is 4.6 Earth years, and the easiest planet in our solar system to compare it to is going to be Earth, because Earth has a period of 1 year. Makes the math really easy. And if we have Earth as our B planet, then the radius is going to be 1 astronomical unit, which means we're just looking for how many astronomical units the asteroid is from the sun. We could simplify this. 4.6 squared equals RA cubed. Take the cube root of each one, and you get RA. RA equals, all right, that's where we get the calculator out. 4.6, 4.6, here's our square button, squared. And then we are going to take the cube root of this. That is going to be that button up there with these calculators. Cube root of our answer. Let me make sure you can see the answer buttons right here. So whenever I push answer, that's where I'm clicking from. Cube root of that answer. The radius is going to be about 2.77 astronomical units. And that is our answer. All right, jumping into the next one. Jupiter, another planet that orbits the sun, has a mean orbital radius of approximately 5.2 AU. How long does it take for Jupiter to orbit the sun in Earth years? So, in this problem, I want to do an example of putting Jupiter on the bottom and showing you that extra step. So if we look what we're looking for here, how long does it take Jupiter to orbit the sun? That is going to be a T. That is a period. So that's period of Jupiter. We're going to compare it with Earth. Earth is 1 year, and Earth is 1 AU. And for Jupiter, it's 5.2 AU from the sun. So 5.2 times the distance Earth is from the sun. So from here, I got 1 over T, 1 over the period of Jupiter, squared, equals, and I'm just going to plug all this into my calculator right here, 1 divided by 5.2, and then I want to cube this number, which is going to be this number right here, answer cubed, and I get, what is this, 0.0071. 0.0071. The next step is going to be to take the square root of both sides. And then I would get 1 over T is equal to the square root of this number right here. So I'm going to plug in my square root of my answer, and I get about 0.084. All right, so from here, we can't just divide or multiply by a number. We got to get t over here. So I got to multiply by t on both sides. And I get 1 equals 0.084 t. And then I would have to divide both sides by 0.084. And I would get t, the period of Jupiter, equals, let's get our calculator back out here, 1 divided by 0.084. It's going to be about 11.9 Earth years for Jupiter to make it all the way around. So again, this is why I don't recommend putting your unknown on the bottom, because then you got to do this little switch around, but it's still possible. All right, one more question like this. Titan, one of Saturn's moons, has an orbital radius of 1.22 times 10 to the 9 meters. Notice how we're using meters here. And there we got meters as well. Excellent. And a period of 15.95 days. Hyperion, another moon, orbits at a radius of 1.48 times 10 to the 9 meters. Same units. Predict the orbital period of Hyperion in days. So the period is going to be in days. We're looking for the period of Hyperion. So we're going to put Hyperion on top. Titan, the period was 15.95. And we want to make sure we keep it the same over here. So if Titan is on the bottom, we would put 1.22 times 10 to the 9. And Hyperion goes on top, so 1.48 times 10 to the 9 here. All right, so, oh, and I almost forgot, we got to cube that. So as we plug this in our calculator, this is going to give us a number. Oh my goodness, I spared it all. This is going to give us a number right here. So I'm just going to plug that in, 1.48. Notice I'm using the E button down here, 1.48 E to the 9. I'm going to divide that by 1.22 E to the 9, and I'm going to get this number. And then I'm going to cube it. But let me plug in a common mistake I see students making. I see students doing this a lot. 1.48 times 10 to the 9, which is this number. Excellent. And I'm dividing it by 1.22 times 10 to the 9. And when you do that, you know, this number looks similar, but I get a completely different exponent here. The reason why is because your calculator did it in order. It did this number times this, and then it divided. It didn't divide by this whole big number. It just divided by 1.22. And then it went and multiplied by 10 to the 9 again. So you got this way bigger number than you needed. If you choose to do this times 10 and then carry it to the power of, you have to use your parentheses around your entire number. Otherwise, your calculator is going to get the wrong order. So let's go back and we'll do it this way, and I'll plug everything in, and we'll do with our parentheses. 1.22 times 10 caret 9. And then we get this number. See, the parentheses it makes the magic happen there. And then we got to cube it. So to the third power, 1.785. All right. So TH over 15.95 squared equals about 1.79. We'll round it. Take the square root of both sides, and you'll get TH over 15.95 equals, all right, we got to get the square root of this. Square root button of our answer gives us about 1.34. 1.34. And we got one last step. You got to multiply both sides by 15.95. to get your TH. Our period of Hyperion is going to be this number times 15.95, or about 21.3. Don't forget your units. In this case, they are going to be days. All right, next we got some questions on Newton's law of universal gravity. I think this question, or these equations, are a little bit easier. Use the table of sun-planet masses. I got my table over here somewhere. Let me grab it. Forgot to mention this at the beginning of our video. You could also look online to find your table. I'm using this one specifically. The gravitational force between the Earth and the Sun. So we're looking for gravitational pull, Fg, and that's going to be big G. I'm going to write big G right here. Big G is going to be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And those units just make it so our units work out in the end. So I'm going to plug that number, 6.67 times 10 to the negative 11, between Earth and the Sun. So I got to get the mass of both of those. So on this table, the mass of the Sun, and it doesn't matter what order you plug these in. There's the mass of your Sun, 1.99 times 10 to the 30. Here's Earth, 5.97 times 10 to the 24. 1.99 times 10 to the 30 kilograms. And make sure your units are kilograms. Times 5.97 times 10 to the 24 kilograms. Divide this by your radius squared. So this is going to be the distance between them. And again, because we're using newtons, we have to use meters. So it's going to be about 1.5 times 10 to the 11 squared. 1.5 times 10 to the 11 all squared. And you just got to plug this in your calculator. All right, so when you see me do it, we are going to just start with big G. And I like pushing equals every time I do a number in scientific notation. It's a good habit to push equals. We are going to multiply that by the mass of the Sun, 1.99 E30. And we got to multiply it by the mass of Earth, so times 5.97 E24. Then we got to divide it by radius squared. So you're welcome to type all this in, but when you divide by a number squared, it's like dividing by it twice. So what you're going to see me do here is I'm going to divide it by 1.5 times 10 to the 11, and I pushed it once, and now I divide it again. Right there. 3.52 times 10 to the 22 newtons. That is a lot of force, but two big planets. Or, sorry, not even two big. One big planet and one very large star. Actually, it's an average-sized planet and an average-sized star, but they're both very large. Two students are standing 5 meters apart. One student has a mass of 60 kilograms, and the other has a mass of 80 kilograms. Calculate the gravitational force between them. Notice this is the law of universal gravity. The idea is everything is going to have a gravitational field and be pulling things to them. So even these two students will have a gravitational force attracting them together. So we got F of G equals, always big G right here, 6.67 times 10 to the negative 11. The mass of both students, 60 kilograms, 80 kilograms. And then the distance between them squared, 5 squared. Plug this in our calculator. Again, we only got one number in scientific notation, so this is going to be a little bit easier when we plug this in our calculator. 6.67 e to the negative 11 times 60 times 80, and then divided by 5 squared. I do it in my head, 25. And that's going to be our answer. I would write this in scientific notation just to make your life a little bit easier. Here we go. Let's count how many spots we move it over. 1, 2, 3, 4, 5, 6, 7, 8. So 1.2 times 10 to the negative 8. And our units are newtons. So two smaller masses will have a much smaller force on each other than two large masses. All right, if the distance between the students was cut in half, how much stronger would the force be? And we can go through and we could do this calculation. The distance would be cut in half, so it would be 2.5. So it would be this whole thing, except at the bottom, I'm going to put 2.5 there instead of 5. Let's run this through the calculator again. Times 60 times 80. And then I'm going to divide it by 2.5 squared. And it's going to be about 5.1, again, times 10 to the negative 8. And there's some rounding differences here, but this, if we cut the distance in half, this should be 4 times stronger. And it's about 4 times stronger. It's a little bit more, must be because of how the calculator was rounding. If one of the students doubled in mass, how much stronger would the force be? And here's the thing, it doesn't matter which student it is. We're just going to end up putting times 2 in the calculator. So let's just e to the negative 11, times 60, times 80, and one of them has to be double the size, so times 2. And then we'll divide it, we'll compare it to the original. So divided by 5 squared. And it's going to be about 2.5 times 10 to the negative 8 newtons. And what you'll notice is, the only difference is we put a times 2 at the top there. So it's 2 times stronger if one of those students doubled in mass. All right, one last question. This one's a little bit tricky. A probe with a mass 500 kilograms is located somewhere in space. A nearby satellite with a mass of 1,500 kilograms exerts a gravitational force of 4.5 times 10 to the negative 7 newtons on the probe. How far apart are the probe and the satellite? So we got our equation here. Doesn't matter which mass we plug in for which one. They're going to exert the same force on each other because of Newton's third law. And we're looking for R here. So we could plug our numbers in. F is 4.5 times 10 to the negative 7. We got big G, which is 6.67 times 10 to the negative 11. You got both your masses, 500, 1,500, and we are looking for R. So we're finding R squared. I'm going to multiply both sides by R squared, and that gets rid of it down here, and it puts R squared over here. And then what I'll have is I'm going to divide both sides by 4.5 times 10 to the negative 7. So R squared is equal to, I'm going to just multiply all these together here. 6.67 exponent negative 11 times 500 times 1,500, and I get this number, I'll do it non-scientific notation, 4 zeros, 50025 divided by 4.5 times 10 to the negative 7. All right, so I got this number, same number here. I'm going to divide it by that 4.5 times 10 to the negative 7, e negative 7. And I get this 111.2 about. So I get R squared equals 111.2. I have a simple last step. I got to take the square root of both sides here. So 111.2 square root. I get my radius. R is the square root of this number, square root of my answer. And I get about 10.5. And I got to think, what were my units? The radius, because we're using newtons with the big G, is going to be meters. So those satellites are actually very, very close together, thinking about how big they are. All right, so that's all I got. Thanks for watching.